Today we are very happy to have Claudia Rham, and she's going to tell us about positivity with gravity. Over to you, Claudia.
Okay, thank you very much. And I'd like to start by, of course, thanking the Tata Institute. Oops, let's see. Okay, for the opportunity to talk. And I don't know why there is a line here. Well, okay. And I also like to thank my collaborators who've done most of the work in everything I'll be talking about today. So just starting with some motivations, as we all know, there's been, well, thousands of years of success, but the past century has been particularly successful with predictions from remarkable theories of the standard model of particle physics and general relativity and the standard model of cosmology, which are in incredible agreement with all sets of experiments and observations. So this is just a few of the type of observations that have been in impeccable agreement, in particular with GR and the cosmological standard model. And I'm not depicting anything on particle physics, but I'm sure we all know about it. However, at the core of all of this success is the will of doing even better and understanding how the models that represent the world so well at relatively low energy could ultimately be embeddable in a high energy completion of quantum gravity. And I know, particularly for members of your group, there's been remarkable success in starting with some quantum theory of gravity, some fundamental theory, and finding some realizations in which we can have some models at low energy which are meaningful. And I think there's been a lot of progress in those directions. The way what I'll be discussing about today is more of a complementary approach where we start our way from the bottom, from the ground, and then we build our way up to trying to see how they would be ultimately embeddable in a high energy completion. So it's simply a complementary approach, and I think there's some value in following both approaches in parallel. So if we start motivated by the observations and the realizations that we have at low energy to try to build up some low energy models which are successful in describing all the observations and experiments that we experience. So we may consider a model which is completely consistent at low energy, both from an observational and experimental point of view, but also from a theoretical point of view. So those models would be completely stable and satisfy some type of requirement at low energy, which are meaningful. And now we'd like to see how those models could ultimately be embedded in a high energy completion. And the surprise is that for some models, we'd actually know that no matter how consistent they may appear to be at low energy, in particular, they may be completely stable. For some of those models, we know that there will never be a standard high energy completion which will accommodate for them. And so what I'll describe is this idea, which is complementary to the Swampland program, although it is slightly different, on how we can put constraints on our low energy effective field theory, simply based on the requirement that it should be embeddable in principle in a standard high energy completion. And so there's various assumptions that comes into stating what I mean by a standard high energy completion. And really what I have in mind is a high energy completion, which is unitary, causal, Lorentz invariance, and is sufficiently local in that it satisfies the Froissart bound. So these are the only assumptions I'm going to put for myself on the type of high energy completion. I'm going to allow otherwise any other type of realization. It could in principle be string theory, or it could be something complementary. And I'm not going to restrict myself on the type of field content that generalize my low energy effective field theory at high energy. In particular, I can have an infinite tower of higher spin states at high energy, and everything I'll be talking about today is completely applicable. So at first, it may seem remarkable that just having some requirements on the consistency of my high energy embedding could have some requirements imposed at low energy, because there should be a decoupling of scales between what's happening at high energy and what's going on at low energy. So I shouldn't really need to know about my high energy completion to do physics at low energy. And that's why we do the physics we do at low energy as we do today. But there's a very notion of causality, which is embedded in the notion of analyticity, which is precisely what makes the connection between some requirements of my high energy completion and some requirements within my low energy effective field theory. So I'm going to go through the derivation of these requirements in a non-gravitational effective field theory first, and then I'll try to see how we can generalize that to gravitational ones, because the situation is a little bit more tricky or more subtle, maybe more interesting when we're dealing with gravitational effective field theory. So to start with, let me imagine that I have, take your favorite model, whatever it is, maybe it's inflation, maybe it's the standard model of particle physics. You define some states in this low energy effective field theory, and you compute 2-to-2 elastic scattering amplitude between those states. And so this amplitude, I can analytically continue it in the complex energy square plane and then Mandelstam variable S. And this low energy effective field theory will have a finite region of validity. This is always the case if you're dealing with a gravitational effective field theory. In the standard model, maybe you would have thought without coupling to gravity, you would have an infinite region of validity. But now we're more thinking in terms of effective field theories. So everything I'll be talking about is imagining that I have a finite region of validity for my low energy effective field theory. So in this region of validity, I can compute my amplitude using the tools that I have for my low energy effective field theory. And then beyond this region of validity, there is still a notion of an amplitude. I simply cannot use my low energy effective field theory to compute this amplitude. But that's okay, the amplitude itself exists. And there may be many layers of physics that I need to include so that I can compute my amplitude to higher and higher and higher energies, all the way up to a fundamental theory of quantum gravity, or maybe here I'm not going to have a quantum gravity, but a fundamental theory of everything at infinite high energy. And so definitely in here, I cannot use my low energy effective field theory to compute my amplitude, but if I included sufficient, all my layers of physics until here, I imagine that I'll be able to compute ultimately some amplitude. Right now, I don't need to know what this amplitude is and what its expression is at very high energy. I'm just going to impose some requirements on this amplitude, for instance, unitarity. And if I also impose on myself the notion of causality, is this notion of causality which manifests itself at the level of the amplitude as a statement on analyticity. So the amplitude has to remain analytic in the complex energy square plane everywhere in the first Riemann sheet aside from the real axis. And it's in order for causality to be maintained. And so I'm happy to discuss a little bit more about this notion between causality and analyticity later if you want to, but this is a standard requirement in non-gravitational effective field theory. In the context of gravity, that becomes a little bit more subtle. But it's precisely this notion of causality, which manifests itself in the statement of analyticity for the amplitude, which allows us to make a connection between some requirements of the amplitude at high energy and those at low energy. So that's precisely what makes the translation between.
Sorry, Claudia, you can ignore this, but I don't work in this area. And when it comes to gravitation, what do you then mean by this notion of causality? That is, because the metric is fluctuating and so on. Is it some asymptotic notion, say in asymptotically flat spaces, that you only get time delays and not time advances?
Yes, exactly. That's exactly what it is. And the whole second half of this talk, I'll be talking about it. Okay. So let me go through it, but it's exactly what you're saying. Okay. And it's really related to what's going on at infinitely high frequencies in principle, which really should see flat space-time as a local metric. But then I'll try to understand what it really means when we're just living at low energy, and these requirements may seem manifest themselves a little bit differently. But I'll go through some of these notions later on. And if I haven't, I'm sure I won't completely answer your question, but maybe we can talk about that later.
Thank you.
Yeah. Okay. So now that we have the notion of, I'll assume really that the notion of analyticity is what translates in that of causality. Now that we have that, we can derive what we call positivity bounds, which are manifest already within the framework of the low energy effective field theory, where it is valid, even though they use some assumptions about what nature is doing at extremely high energies. So if I start with the notion of unitarity, which is embedded in part of it is embedded in the optical theorem, it tells me that the discontinuity of the branch cut along the real axis has to be positive. This is manifest from the dispersion relations. And so the first requirements that I'm gonna put on myself is that unitarity is valid up to infinite high energy. And so the discontinuity of the branch cut should always be positive everywhere on the real axis, on the positive side of the real axis. Now, if I further assume Lorentz invariance as a fundamental theory, then I should also have crossing symmetry, which tells me that if I consider the S or the T or the U channel, they should all be equivalent. And that the branch cut, which is on the negative part of the real axis, this is really related to the U channel system. And so the imaginary part of the branch cut, the discontinuity in here should be positive as well. So that's what the notion of unitarity plus Lorentz invariance tells me. Now, in terms of causality, which I use as analyticity, what it tells me is that I can perform a Cauchy integration formula to compute the amplitude, or it'll be better for us to compute some derivatives of the amplitude at very low frequency, at low energies. And this is related to some Cauchy integration formula, integrating over the branch cut or the discontinuity of the branch cut and taking out some poles. These are the poles living within the low energy effective field theory, which we can compute. So this is just Cauchy integration formula. But now if I also assume locality, and really what I'll assume is the Froissart bound. So even if I don't have a massive particle, if I'm dealing with massless particle, I'll still assume that nature is sufficiently local so as to satisfy the Froissart bound, and so that the amplitude doesn't grow. If the amplitude is polynomially bounded, then it's been shown that it has to satisfy the Froissart bound in this sense. And so when I take the arc here and I send it to infinity, the contribution at infinity of those arcs will go to 0, and I can therefore relate the second derivative of the amplitude at very low energy with the integration of the discontinuity of the branch cut on the real axis, which has to be positive. And therefore that tells me that at low frequency, low energy, the second derivative of the amplitude has to be positive. So this is really just
the Froissart bound was at every fixed t.
Yes, that's at a fixed t, exactly. So this is satisfied at fixed t. You can take it here if you think of it. You can take a t0 if you want to. You can take it at t all the way to m squared if you want to. That's right, but that's at fixed t. And so this is satisfied in string theory, for instance. So even in string theory, you have typically enough locality so as to satisfy the Froissart bound.
And this is at every fixed physical value of t.
That's right. Sorry, in the not physical, in the Mandelstrom region. So where it's analytic still in t. So it's from t positive until m squared.
4m squared.
Yeah. No, just actually just m squared. Just m squared. For s it goes till 4m squared, but for t just till m squared. That's the region of analyticity in the.
You're not considering the large Mandelstam ellipse.
The large Mandelstam.
Sorry, the large Lyman-Martin ellipse. You're not considering convergence there. I mean, the convergence there is up till 4m squared.
For t itself.
Yeah.
You have a pole at you have a pole at t minus m squared, right? So I don't want to go past this pole.
Oh, you have a bound state at t equal to m square.
Yeah, yeah.
Ah,
You
okay.
have a massive particle here. I'm just imagining massive particles, and then you have a t-channel pole that will go like 1 over t minus m squared.
Sorry, there's an elementary confusion. If I did equal mass scattering, would the convention I'm used to would be that t would be for physical equal mass scattering, t would be negative. Is that right? Is that correct?
That's right. So
Okay.
here I'm taking t is 0, and that's right.
So this Frost-Round bound is obeyed when t is negative or t is positive?
No, you're right. When t is negative, t is minus epsilon. Yeah. So t goes to 0 from the negative side.
Right. Thank you.
Yeah.
Sorry,
and
sorry, I'm really sorry. Very elementary question. Sorry. Just in terms of complex analysis, in that equation, you have t equal to 0 on the left-hand side. Are you also taking imaginary part of a as a function of mu and t, and then setting that t to be 0 on the right-hand side? Is that correct?
That's right.
Okay.
So,
okay.
And I should put a minus here.
Okay, fine. I got it. Thank you.
Yeah. So here, that's right. You
Okay,
have
fine. Thank you.
Yeah. So this mu is just a substitute for the s, right? When I do my Gaussian integration.
Thank you.
Okay, so this is nothing new there. It's really just following all the work that has been done in the 60s, and that's been already pointed out quite a few years ago, that those type of relations had to be satisfied if we wanted a high energy completion to be standard. And that's what I mean about standard high energy completion. So just to conclude, I want at low energy, the second derivative of the amplitude to be positive at a fixed t negative or going to 0. Now we can do a little bit better than that, in the sense that in that branch cut here, there are contributions from the loops of the field at low energy, my light field loops, up to a given cutoff, and up to once I reach my cutoff, I also need to include the contributions from my high energy, my heavy states that are not present in my low energy effective field theory. So I can compute everything up to that cutoff, and from the cutoff on, I need to stipulate what precise physics comes in, so as to restore maybe perturbative unitarity, or to restore all the conditions that I want to impose on myself. And that I can't, without stipulating a precise, at least partial high energy completion here, I can't compute the contribution to the branch cut there. But what I know is that the contribution to the branch cut from the cutoff all the way to infinity has to be positive by itself, and the contribution to low energy of those light field loop has to be positive as well. So there are some improved positivity bounds that we can also stipulate, which are a little bit stronger. Instead of saying that the second derivative of the amplitude at, let's say, very small s has to be positive, it actually has to be better than positive. It has to be greater than the contribution from this part of the branch cut, which itself is, we know, is positive, because the remainder is just the contribution of the branch cut from the light and heavy loops, which have to, by themselves, to be positive. So this improved positivity bounds, we'll be using them later on, and it allows us to push those conditions a little bit further. But before I go into looking at particular examples where I can use those positivity bounds, let me just say that when we're talking about subluminality at low energy, at the very least in non-gravitational effective field theories, this is just a consequence of those positivity bounds. And sometimes we have forgotten that they were simple consequences of those positivity bounds, but that's simply what they are. And the standard example is, as you all know, this is all basic, of course, if you shine light through, let's say, some water, then for light at frequency, which is comparable to the intermolecular distance in that medium, it's going to get the speed of light in that medium is going to be affected by that medium, and therefore we'll have that the speed at a particular frequency is related to the real part of the refracting index. Now, to some extent, this refractive index is related to the scattering amplitude itself. And those notions of unitarity and causality, as we had them before, they apply as well to this refractive index. In particular, the notion of unitarity tells me that the imaginary part of this refractive index has to be positive for all frequency, all the way up to infinite frequency. And then using causality through the notion of analyticity, and this is really just standard textbook formulation. If you perform Cauchy integration, you can relate the real part of the refractive index at 0 frequency to that at infinite frequency with the imaginary part of the refractive index, which is positive definite. And this is really what tells us at the end of the day, when you relate that back to the speed, that the phase velocity at 0 frequency, but small frequency, should always be smaller than the phase velocity at infinite frequency, which is really the front velocity, which is the speed of propagation of information. And this is the quantity that has to be bounded to remain causal. But that there's a direct link as we know, at low frequency, the speed, the phase velocity has to be subluminal so that causality is preserved. And this is typically what we do always, but sometimes we kind of forget that it was coming through these particular assumptions that the notion of subluminality at low energy was related to that of causality.
Sorry, and can you conclude that the phase velocity at every frequency is lower than that at infinity, or just at 0?
At every frequency, yeah. That you can do as well.
Thank you.
Yeah. So it has for any omega here, you have to have it smaller than at infinite frequency. Okay, so just to summarize this standard picture. If you, in a non-gravitational effective field theory, if you have some type of, I would say, reasonable assumptions at high energy, particularly that of unitarity, causality, then you can actually derive, I showed how to derive one particular positivity bounds, but the notion of unitarity is really a statement on the coefficient of every single partial wave, coefficient in the partial wave expansion. And so you really have an infinite number of conditions that have to be satisfied. And so those translate into an infinite number of constraints that have to be implemented within the regime of validity of your low energy effective field theory. And one of those constraints, typically for non-gravitational effective field theory, translates or manifests itself in a notion of subluminality. But there's another infinite number of constraints that can be implemented at low energy. And just to give you an example of how this is useful for non-gravitational effective field theories, before I move into gravitational examples, this is some work done by Changkyang Zhou and Zhou in the past 3 years or so, just applying this to physics beyond the standard model of particle. In particular, they've been looking at dimensionate beyond the standard model for vector bosons interactions. So it doesn't matter too much how they parameterize it. This is standard in the beyond the standard model EFD type of parameterization. So you have a lot of different operators, and then asking for those type of effective field theory to satisfy the positivity bounds, as I mentioned them before. It tells you that the coefficients here, the coefficient Fi of the dimension 8 operators, have to be living within some particular region of parameter space. These are, again, just examples, but in blue are the expectation of the regions which are compatible with current experiments or future experiments. And then in green are the regions where you are compatible with the positivity bounds, as I mentioned before. And so the only thing I want to illustrate here is how complementary these positivity bounds are with current experiments or observations. And these positivity bounds, from the point of view of subluminality, it might be something that you thought was expected and quite maybe trivial, but a lot of those positivity bounds, they really give you some additional information which wouldn't have been manifest at all had you just stared at the low energy effective field theory without some input from this type of standard high energy completion that you wanted. So this is just the motivation. Now,
could I ask, do you expect that if you look harder just at low energy phenomena, you would find a derivation of each of these bounds purely sticking to low energies?
So I don't myself, but I've been talking with a few people, and they always think one should be able to. Personally, I don't, because it really gives you some insight of what's going on at high energy. So definitely, if you're just interested in, let's say, stability at low energy, this is not something manifest. I mean, the positivity bounds are really much more than just asking for stability of the low energy effective field theory and let's say subluminality. So there are conditions in those positivity bounds here, which I can't translate into something which I can say why that has to be the case just from the low energy effective field theory. I don't see anything wrong with being outside this region in here. Let me just, maybe for those examples, myself, at least, I can't see anything wrong by being in that point of parameter space. It's not like this theory would be unstable. It's not like you have the impression you generate caustic more here than you would do here or anything like that, which is obvious.
But could it be that if you looked harder at low energy causality, more complicated experiments with low energy causality, you'd find that they were violated outside, or is that impossible?
I think that's impossible. I feel that, because the notion of causality, at the end of the day, you can have subluminality. And if you impose subluminality in a non-gravitational setup, that's one condition. And yet that's sufficient to satisfy causality. So I find it hard to understand how, for all of those bounds, for this infinite number of bounds, being outside some of them will necessarily lead to a violation of causality.
Thank you.
But it's possible that, I mean, it's hard to prove that it can never be the case. So all I can say at the moment is that the connection is not straightforward. I can't see that we should have guessed those just from looking at it from the bottom perspective.
Could I just say one more? I'm sorry. Maybe afterwards. Please go. Yeah.
But I think related to your comment, in the example I'm going to show you, I mean, there's direct connection, which you thought you can start looking at the low energy EFT and seeing that there's some particular feature that happens if you're not in that region, and then from there trying to connect with being outside that region. Maybe that's really related to having violating the assumptions at high energy. Okay, so this is all I wanted to say for non-gravitational effective field theories, and then we can go through many different examples, and there's a whole community working on gravitational and non-gravitational examples now. For the rest of today, I just want to be a little bit more concrete, and I'll focus on the application to these contributions to the weak gravity conjecture. So I'm sure most of you are much more expert on the weak gravity conjecture than I am. So just to give you a quick cartoon back of the envelope motivation of why this weak gravity, how this weak gravity conjecture came from. If we consider any beyond the standard model U1, no matter what it is, then we imagine it has a field strength tensor like that, contribution. And now black holes can be charged with respect to this U1, and I can consider some extremal black hole, which in units of Planck scale, its charge is equal to its mass. Now, if I let this black hole evaporate in order to avoid any naked singularity, it has to evaporate so that the charge remains smaller than its mass. And therefore, for that process to happen, I need someone to carry on the leftover charge. And so we need, for every U1 beyond the standard model, that there are massive charged particles which charges are larger than the mass in units of Planck scale. So that's the very rough story. And I apologize if I offend anyone by being too simplistic in this description. It's of course far less trivial than what I'm trying to depict it here. Now,
Claudia,
of course,
sorry, you have to go on, and I'm actually not as well informed as I should be about this conjecture, but this should apply then for both electric and magnetically charged particles under the U1, I presume.
I
mean,
so,
just in case, you know.
So probably other people attending the talk can answer that better than I can.
Okay, no, that's fine. That's fine.
Yeah.
Yeah, there's a magnetic version of the weak gravity conjecture, which relates to the UV cutoff in the theory, and I don't think that's
okay.
Yeah. So this magnetic version I will discuss about, but yeah, and I don't know if I answer your question.
Okay,
We'll see.
that's fine. Please.
Okay, so of course for for the electromagnetism U1 we're used to, this is manifestly satisfied for the electron, but we want to apply that. That has to be the case for any other U1 that makes this beyond the standard model. So now it's possible that nature has its own ingenious way to dealing with it. In particular, if you consider the effective field theory for any U1 that makes this beyond the standard model, in addition to the operators that I wrote down here, you'll have an infinite number of operators that will come into the EFT. And I just wrote a few of them which are relevant for my discussion, but there's really an infinite number of operators that will contribute. Now, those operators by themselves, they will redress the notion of black hole mass and charge, and they do so in a slightly different way as well, so that when you account for the leading operators that come into the EFT of any U1 coupled to gravity, then the new extremolity condition is no longer just that the charge is equal to the mass. It's not just one, but you have corrections which depends, of course, on the coefficients of those operators, and they have a particular expression. Okay, this is not particularly nice, but what happens is that if this EFT is such that those coefficients A and B are such that this contribution is always positive, then the new extremolity condition will always be satisfied. So you can have extremal black hole evaporate, then the mass decreases, and then the black hole which has evaporated is always manifestly sub-extremal. So you can satisfy kind of the weak gravitation conjecture, letting black hole evaporate without leading to any naked singularity, and yet without needing to postulate a massive charged particle necessarily with charge larger than its mass. Really, the black hole themselves satisfy this relation, or in other words, the operators that come into the EFT, which may or may not have accounted from having integrated out massive particle of charge larger than their mass, but those operators always lead to satisfying the sub-extremality condition. So in a sense, this would be a very natural way to understand the weak gravity conjecture. And if using the positivity bounds, we could state that for any U1 EFT that is embeddable in a standard high energy completion, we always need those coefficients A and B that satisfy the relation, this being positive, then we would kind of prove the weak gravity conjecture. So the weak gravity conjecture will be ensured for any theory that is embeddable within a standard high energy completion. So what we'll try to do, and this is not me, this is something that's been done successfully by many people in the literature, is to try to use the positivity bounds to see if we can require the demand that this quantity being positive. So
sorry, when you say the weak gravity conjecture would be proved, you mean sort of it for near to Einstein gravity? The curve could bend around again far away, right?
Oh yes, yeah, no, absolutely, yeah, absolutely. So yeah, this is always assuming perturbative behavior, absolutely, yeah. Okay, so now let me take this EFT, and I have, I guess I have equivalent to photons. I have graviton in this low energy EFT. So I can compute a scattering amplitude, let's say between 2 to 2 photons, like so. And I'm not going to stipulate too much what precise polarization I'm going to use for my photons, but I can choose a polarization for my incoming 2 photons in such a way that the contribution to the amplitude, or to the S square contribution to the amplitude here, is precisely that relation that came in correcting the extremality condition of the black holes in this EFT. So this feature by itself seems to be very closely linked to positivity bounds. But the only thing that happens as soon as you're dealing with gravitational effective field theory, as we're doing here, is that in addition to the standard contribution that we can deal with, there's a T-channel pole. This T-channel pole here is related to the fact that you have a graviton exchange coming in. You can't, as soon as you are dealing with a gravitational effective field theory, you can't prevent the graviton from starting to play with you and contributing to the amplitude. So this is entirely to be expected, and that would happen also if you had if gravity was a lower spin particle. The same type of thing would happen. But as soon as you're dealing with gravity, which is a spin 2 particle, the residue of this pole grows like a square, which itself saturates the Froissart bound. And so unlike what you have if you have an exchange of massless particle or spin less than 2, you can't subtract this contribution from the amplitude, because the whole amplitude itself, we assume, satisfies the Froissart bound. So you can't remove something that violates the Froissart bound and expect the remainder to satisfy the Froissart bound. So this is the difference between including graviton exchange. And so we have to deal with this T-channel pole in principle, and that by itself, because it grows like a square, thus compromises the applicability of the positivity bounds. So this in principle contributes to the positivity bounds, and asking for this contribution to be positive at T0 is really completely dominated by this contribution there. So
sorry,
yeah,
clarification. So this choice of polarization that you made, it exists in every dimension or a specific dimension?
I think it is dimension dependent. Here I made a particular choice this is in 4 dimensions. I think in few dimensions it's a little bit easier, but I think in any dimensions you can find some particular polarization, so that at the end of the day, some subset of conditions that you're gonna need to impose is precisely linked to what you end up here from the modification of the extremality condition of black holes.
Thank you.
Yeah. So yeah, all of yeah.
So isn't it conceivable that if you use other polarizations, you would get different combinations, which and then let's say you get inequalities for those other combinations, and those will not necessarily correspond to the ones that come from weak gravity conjecture, let's say. I mean, I'm just
So the other ones, I'm being very specific. I chose a particular polarization here so that you get that condition. Then if you just say plus plus goes to plus plus, for instance, you get a slightly different condition, which has to also be imposed in addition to that. So all processes had to satisfy the positivity bounds. So it's not just that this has to be satisfied. Other conditions also have to be satisfied.
But is there a reason why the weak gravity conjecture kind of picks this out? Or is there any way, in other words, to get other things from similar black hole type considerations?
At this level, I would say it's the fact that you can at all from positivity bounds pick out such a contribution is very suggestive that it should be linked. The two should be linked. I mean, with respect to your other question, can you repeat maybe?
Is there a way? So as you said, if you pick different polarizations, you might get inequalities which look a bit different from this. I was asking, is there any way of understanding those inequalities along the similar lines as weak gravity conjecture, the way you explained this?
Yeah, I would say not as much, and I think that's kind of related to the question before on whether those positivity bounds you could have seen them as consistency relations at low energy. And I think typically it's hard to derive them just from a point of view of the low energy effective field theory, or even understand what they are. I mean, one of those is also related to asking that the speed of photons on backgrounds that spontaneously break Lorentz invariance on a specific class of backgrounds, this should also be subluminal. So there are some conditions like that which seem to be linked with something physical at low energy or some consistency at low energy. But some others, they don't seem to be so intuitive to understand, even the other ones that I haven't written down.
Thank you.
Okay, so
Hi, can I ask a question?
yes.
So in the because we are taking a small t limit, shouldn't you look at the full iconal contribution to the first term? So you can just resum all the ladder graphs, and you can resum all the ladder diagrams for the gravitational exchange. So the first here you're only looking at the Born approximation, right? For the first
Yes.
term,
Okay. Yeah. Okay. So very good. So this is related to something I'm not going to discuss too much, but I'm happy to do later if you want to. Okay. So this is in 4 dimensions, and you can indeed resum all of the diagrams and kind of do an iconal approximation. That won't affect this this contribution so much, because there's a physical pole there. There's a physical process. You're still gonna have essentially the same thing coming in here. It's very different as compared to what would have happened had you done that in 3 dimensions. Perturbatively, you're absolutely right. The leading contribution from the 0 kk mode was from the massless graviton in 3 dimensions would have given you that. But then you can resum all the ladder diagrams in 3 dimensions, and that would have actually resummed into something where you don't see that pole. But you have other issues when you do these iconal approximations in 3D. So in 3D, you can think of it as not quite as a pole itself, but then there's an imaginary part that comes in instead when you do this resummation that you need to be instead careful with.
Okay, so the tension with this horizontal bound is dominated by this term, and it will not be affected by the in 4 dimensions. It will not be affected by the full iconal. Okay.
That's right, exactly. So in 4 dimension, you expect this to be the leading contribution to that bound. That's right.
Thanks.
Yeah. Yeah, very good. So this is very relevant to the discussion, and it's also kind of some motivation. Some of this reasoning were motivation for for that paper, for instance, into why we can start by trying to understand what happens if we were to apply the positivity bounds to the T-channel pole subtracted amplitude. So let's ignore this contribution for a second, because the results are so remarkable that they may seem to be linked to something very fundamental. And once we can understand what happens in the case where we ignore that, we can then try to put that back in and see the effect of this T-channel pole by itself. So there's been some motivation, some very good motivation from based in other dimensions, or based on some assumption about the behavior, the rigid behavior at high energy, onto when or how we could possibly ignore that pole. For now, let me not give any motivation. Let me just ignore it from the outset and try to see if, because the amplitude, the remainder of the amplitude does behave like that, if I can simply use the positivity bounds, which themselves would indicate that this contribution here has to be positive, and therefore that would go within the direction that you need to have, at least perturbatively, for the EFT corrected black hole to always satisfy the extremality condition. If you start with extremality condition and you let them evaporate. So by itself, this would be some type of proof, at least perturbative proof, for the weak gravity conjecture in any type of effective field theory, if you can neglect this T-channel pole by itself. And then if you further think, and this is more of a complementary approach, and a different way to see the same problem. If you thought of this EFT, the Euler-Heisenberg EFT that I wrote down, as having come from integrated out a particle of mass m and charge q, and those coefficient a and b will be roughly of order 1 in that case, then this positivity bounds will actually impose that the mass has to be smaller than some order 1 quantity related to the charge of the particle. And so that would be another way to think about the weak gravity conjecture. And that's really, if you think of this Euler-Heisenberg EFT as having come from having integrated out some massive charged particles. And the spin of this charged particle is irrelevant. It's been shown for many different types of spins, 0, I think half and 1 in that paper. So all of that is very, I would say, is very indicative that there seems to be a strong link between the positivity bounds, or the applying the positivity bounds to the T-channel pole subtracted amplitude, and some realization of the weak gravity conjecture. So what I'll try to do for the next few slides, and I don't know how much more time I have, so interrupt me when you want, but what I'll try to do for the next maybe 5 minutes or so is simply to understand how well motivated it is to apply the positivity bounds to the T-channel pole subtracted amplitude. And for that, I'll apply it to the only U1 example that I know is realized in nature for now, which is electromagnetism. So to be clear, because sometimes I think I may be a little bit confusing what I mean. To be clear, of course, QED and electromagnetism has a charged particle which satisfies by itself the weak gravity conjecture. So I'm not trying to prove the weak gravity conjecture in QED, that's already manifest. All I want to do is look at the amplitude in the context of QED and see how justified it is to impose positivity bounds on that amplitude for QED to the T-channel pole subtracted amplitude. Because if it seems justified in that case, then
I have a question. So when you said indicate out a particle, you mean indicate out a scalar particle, or is the analogous? Is the analogous combination for indicating out a, say, a massive vector or something wrong?
Yeah, so you can do in that paper, I believe they did it for scalar, fermions, and spin 1.
Okay,
so they have various examples, yeah. Yeah, so it seems to be quite generic. and you want to stop the spin 1, right? There's reason why you don't want to go beyond that. So for all the examples that you can consider, it seems to be working remarkably well. Yeah. Okay, so let me try to apply this logic to QED. And just to set things up, at low energy, in the case of QED, at energies below the electron mass, I have the same similar Euler-Heisenberg effective field theory, when now M is related to the mass of the electron and Q is related to the charge of the electron. And if you go above the electron mass, then I know exactly what happens. Really, it's QED. I just reintroduce the electron and it's minimally coupled to gravity. And I can trust this kind of partial UV completion. It's not a UV completion by any stretch of imagination, but it generalizes this low energy Euler-Heisenberg EFT. And I can trust it up to a given scale. I don't know exactly what that scale is a priori, but I know that it has to be related to the Planck scale somehow. So maybe it's a bit lower than the Planck scale. I don't know exactly, but if I were to send the Planck scale to infinity and switch all the gravitational effect off, then I would expect QED to be a valid effective field theory all the way to as high energy as you want in some sense. So I'll try to apply this type of reasoning to QED coupled to gravity, first within the low energy effective field theory, and then including back the electrons in the game.
So sorry, can I just ask, there's also a Landau pole problem with QED per se, right?
Yes,
where does that lie?
It's so high. It's
very
so
high.
high.
Sorry, I should have known that. It's very high.
Yeah.
Okay.
It's so high that it's way beyond the Planck scale. So
okay. Thank you.
Yeah. No, so yeah, we don't. For here, you have so many more other problems before you get there. That you don't need to worry.
Okay.
But yeah.
Thank you.
That's right. Yeah. Okay. So you may not want. It depends on what you want to do, right? You may not want to send. If the Planck scale goes to infinity, this cutoff may not be infinite. Mm-hmm. But for all intents and purposes, it's very large. Mm-hmm. Right. Okay. So if you work below the electron mass, at energy scales below the electron mass, then the amplitude is exactly what we had before. We know, it's always something like that. And we know that this contribution here was coming from the contact terms, which are just pure photon types of interactions after you have integrated out the electron. But you don't need to work below the electron mass. You can actually work below the cutoff and simply include back the electron in the game. And so instead of computing this contribution from the contact term, you can include the electron loops, and that they will lead to the branch cut. These are now part of, if you include the electron loops in the game, they are part of your light fields, and they are part of the branch cut, which include the light field loops. Now, because we can trust the EFT of QED, minimally coupled to gravity up to some cutoff lambda, I can compute this part of the branch cut and remove it. And really the positivity bounds that I have to impose on myself are not simply that this contribution is positive, even if I ignore the T-channel pole. So remember here, I'm just trying to understand what would happen if I ignore the T-channel pole. It is not just that this contribution is positive. Really, I need the second derivative of the amplitude to be larger than the whole contribution of the electron loops or the whole branch cut. So it's not just the electron loop, it's the whole contribution from everybody to the branch cut all the way up to some cutoff scale. And so I'm going to spare you some of the details, but you can look at what this condition will be. And the relevant contribution to the amplitude or second derivative, if you ignore the T-channel pole, is a contribution that is dependent on the cutoff itself. So if you send lambda to infinity, then this contribution here by itself would be positive and it will be fine. But because we're dealing with a gravitational effective field theory, there's a contribution from gravity itself, and it is negative. And it's not so surprising that it is negative, because it comes hand in hand with also a T-channel pole, which has been removed or at least ignored. So because of the gravitational contributions, which is negative, part of this improved positivity bounds, you can't send this scale lambda to infinity. And unsurprisingly, you have to send it to a scale which is sensitive to the Planck scale. But the surprise is that this scale is parametrically smaller than the Planck scale. It's actually way smaller than the Planck scale. And if you took the mass of the electron and the electron charge here, it would be roughly 1000 TeV. So now, if you take these bounds at face value and you assume that it is consistent to apply the T-channel pole subtracted positivity bounds, it would seem to suggest that you need to have a cutoff for QED minimally coupled to gravity, which is as small as 1000 TeV. And this is okay, it's higher energy scale than LHC, but it's next generation of accelerators. It's not so far off in the future. And I would tell you that you would really need to see the new signs of quantum gravity effect at such a low energy scale to be consistent with this embedding within a high energy completion if you were allowed to simply subtract the T-channel pole, remove the T-channel pole. So if you consider, here I'm calling them as compact bounds, because these are motivated by imagining what will happen if you were able to compactify those bounds. So either you consider that this is really what happens, and QED minimally coupled to gravity requires new interactions with photons that happen at an extremely low energy scale, as low as 1000 TeV, even for weakly coupled UV completions. So that's one of the first possible outcome. Or something that I haven't really mentioned before, but let me just mention it here. The moment the contribution to the improved positivity bounds I mentioned were coming from the contribution to the branch cut, which were at leading order in the Planck scale. Assuming perturbative, they were perturbative. They are a higher order contribution that would go like 1 over m Planck to the 4. And it's possible that if you included those, they would help into reversing the sign of the contribution in the
I have a question.
Yeah.
So like this, the magnetic charged version of this new physics scale sounds problematic, no? Like, why is that okay? As in, if the E was like, if the E was 0 or something, I'm confused.
So here I'm very concrete. I'm dealing, it's a specific example of QED where E is, I mean, you can take it to be 1 over 137. This is what it is. It's for the specific case of QED minimally coupled to gravity, where m is the electron mass and E is the electric charge. So that's a specific example I'm applying it for, and I'm not applying it for to check whether the weak gravity conjecture is satisfied in this case. I know that it is satisfied, that's all absolutely fine. I'm just using it in that case to understand what the consequences are in applying positivity bounds to the T-channel pole subtracted amplitude.
Maybe what I intend to ask is, like, does it give a scale for looking for magnetically charged particles? Because you haven't found in physics up to some scale.
So you want to do the same thing for E being the magnetic charge?
Right.
Yeah.
And the absence of any physics would probably give a bound for, like, or does it? Am I confused with
Yeah, but I just want to apply it to a concrete model that knows it is present here. So I mean, I know QED exists, and I should be able to couple it minimally to gravity up to a scale. That I know for sure.
Mm-hmm. Okay, and okay, maybe, so can I ask you a different, like, unrelated question? So, is there also a statement of what this AB bound implies in, say, holography or something?
So this upper bound here?
No, the bound about A and B coefficients we wrote earlier.
Yes, that's a good question. I don't know the answer of that. I'm sure other people in the audience know the answer to that better than I do. Yeah, you want to see that from the holographic picture?
Yeah, like usually higher derivative corrections give some bound, right? Say for viscosity or whatever.
I know one paper by Mehrdad Mirbabai, which sort of in some context gets this bound from holography using positivity bounds and conformal correlators.
Yeah, I think.
Okay, thanks.
I think it. So Mehrdad had that paper, but then he retracted it because.
Oh, I'm sorry, I didn't know that. I'm sorry.
Yeah, deep down in his assumption, he still assumes the presence of charged particle with mass smaller than their charge. So I think yeah, he's going into that direction, but at the end of the day, it is not entirely clear how much of the conclusion he had were related to just using holography or putting part of the original assumption, the original conclusion into the assumption. That's the paper you're thinking from
2 years ago, about something like 2 years ago.
Yeah. So yeah, I think it's worth talking with him about it. Yeah, have a look at the comment he put on the archive because he retracted it with some comments related.
Thank you so much. Yes.
Yeah. I think it is it is a very interesting question, and I don't know that all the answers are clear at the moment. But I think it's still very much ongoing work. Yeah. Okay.
Sorry, Claudia. I'm sorry. Yeah. I need to ask you an elementary question, but you can answer it later or not at all. Which is, you know, I'm missing the chain of logic in that you have the full amplitude with the T-channel pole, and there's a positivity argument there.
That's
Why
right.
should there be a positivity argument once you remove the T-channel pole? I mean,
that's right. So this is exactly the key. Why there should be one.
Yeah.
Zeroth order answer is that it seems so. This is so closely linked to the weak gravity conjecture.
Yeah.
It seems to be too good. It seems to be like it shouldn't be an accident. I mean, it's so indicative that it makes us want to try to understand if really this thing is just a red herring, and for a reason or another we can ignore it. I think that's a zeroth order 11 answer. Now, in those papers, there's been with some additional assumptions. For instance, in this paper, there was an assumption that let's imagine I compute this amplitude, but I'm working in 4 dimensions where one of the spatial dimensions is compactified. So it's really, I can think of it as 3-dimensional gravity with a zero mode and an infinite number of Kaluza-Klein gravitons on top of that. Now, the only T-channel pole I should have in 3 dimensions is that of the zero Kaluza-Klein contribution, but it's not physical in 3D. So it should be removable. And that's related to the discussion we had before. Actually, you see that perturbatively, but if you resum an infinite number of ladder diagram, you can actually, that this contribution can be removed in 3D.
I see.
So this is some argument here. Here they have some other type of arguments, which I think are personally, I think are better motivated. But let me just say in here, that's what they assume. And then, so you can say, well, let's imagine I have a 4D amplitude. For a while, I'm gonna regularize it in 3D, perform my amplitude in 3D, and then bring it back to 4D. What's wrong with that? I can do that and then apply my positivity bounds, and therefore this contribution should be irrelevant.
I see. I see.
In some other papers in here, they are able to justify it a little bit more from string theory realizations, where the contribution of this T-channel pole should be weak compared to those ones. So yeah, it's not only that it's implying suppressed, but if you are in a tree-level weakly coupled completion, then actually the contribution of the T-channel pole is always going to be suppressed compared to that. In here, note that we're not quite in a tree-level weakly coupled completion, because the contribution to the FT there is coming from integrating out loops of gravity. So we're not quite in the same assumption that we had in here, which is why we're not satisfying that.
I see.
Thank you.
Yeah.
Thank you.
So there are some motivations onto why this may be justifiable. All I want to do is understand how justifiable it is in the only case I know is manifest in nature. And that's all I want to do. And if it is, if it did work out in QED, then I would say, well, there must be really some truth in those argumentation, and that's really what we should be doing ever. But because that's not going to be the case, at least I don't think that's the case in QED, that's my intake on that, then I would say we have to be careful about this line of reasoning, and in principle this contribution could be important and therefore spoil the applicability of the positivity bounds to the proof of the weak gravity conjecture. Yeah, so I mean, I guess this is in a nutshell all I want to say.
Oh, no, thank you so much. Yeah.
Yeah. Okay. Maybe you can tell me for how much longer you're allowing me to talk, and then I can adjust accordingly.
Abhijit is master of ceremonies.
Okay, let me continue talking, and then you, and everybody has disappeared.
Yeah, in general, we're very flexible about time. So please.
Okay. Okay, thank you very much. That's very kind. Okay, so this is what a class as compactified bounds. It's assuming you can take the amplitude and subtract the T-channel pole and then apply the positivity bounds to the remainder of the amplitude. If you do that, either the outcome is that the cutoff for QED minimally coupled to gravity is less or equal than 1000 TeV, which I would argue is really low for quantum gravity-ish type of effects. Or one thing I haven't quite mentioned, but it's a technical possibility, is that the contribution to the branch cut that I computed before were coming from the leading order in Planck corrected terms, but they are, of course, higher order terms. And if I allow for those ones to contribute, to dominate over those ones, then I could allow for the cutoff to be as large as you want, really. But for that to happen, you need those high order operators to come in at a very low scale. And in a sense, this would happen if you imagine that you have these operators that are coming from having integrated out a large number of other species, which is what makes those contributions as important or dominating over those ones. This is fine, but it has to be so many species that at the end of the day, you need a very large number of species. And this can only be the case if at the end, the mass here of the electron, or and that's applicable to other any other U1 beyond the standard model is larger than the number of species that one over the number of species that you have integrated over. And bear in mind that let me just say this m Planck over square root n star is actually the effective cutoff of the FT. And so it only works if E is relatively small, and therefore you need to have M smaller than m Planck over square root n star and larger than E times the same quantity. So the region of flexibility is very limited. Yeah, sorry.
No, when you included higher order corrections in m Planck, there could be gravity loops, etc. also, right? To modify
yes, but
the behavior at s equal to 0 to logarithm and other.
Yeah, those are even more suppressed. Yeah. I mean, you can have graviton loops as well, but these are even further suppressed. Yeah. So that's a logical possibility, but if you want to have this type of reasoning and have anything to do with the weak gravity conjecture, you're even putting yourself in a even more constrained scenario, because I mean, this is really you have an upper bound rather than a lower bound on the mass. So it seems very much in tension with the type of things you wanted to do to solve the weak, or to prove the weak gravity conjecture.
Yeah. I mean, sorry, this goes totally in the opposite way, right?
That's right. That's right. It goes totally in the opposite way. So right. It's mathematically, it's something. It's a possibility. But if really that's what you want to do, then let's not even look at those argumentations to prove the weak gravity conjecture.
Right.
Yeah. So I would say the outcome is either the first one, or really the intake I'm going to take on all of that is that applying the positivity bounds to the T-channel removed subtracted amplitude is not sufficiently justified. You may need extra assumptions, and in the case of 3D minimally coupled to gravity, probably those additional assumptions are not satisfied. For instance, they come in from having integrated out loops of electrons rather than just a tree level completion. In both cases, it's weakly coupled, but having weakly coupled, as in the case of 3D, is not sufficient. You need more than that. And so the intake I'll take on this is that as soon as you have a T-channel pole in your amplitude, you can't simply apply your positivity bounds to the remainder of the amplitude. You have to account for this contribution into the amplitude as well. And so what it tells you is that the second derivative of the amplitude shouldn't necessarily be positive definite. You can allow for it to be slightly negative by an amount which will go to 0 when you send the Planck scale going into infinity. And this type of argumentation was actually shown to be precisely what was later found out in a nice paper where they used much more bootstrapping arguments combined with these positivity conditions. So in the context of applying this positivity bounds to the weak gravity conjecture, my intake on that, and everybody's welcome to take their own intake, but my own intake on that is that you can't simply apply the T-channel pole subtracted positivity bounds. You need to allow for a contribution, a potential negative contribution to the positivity bounds that is manifested from the presence of the T-channel pole. And so having a standard high energy completion doesn't tell you that this quantity should necessarily be strictly positive. You can have a small level of negativity being involved, which is such that it goes to 0 when the Planck scale goes to infinity. And the precise scaling, you can kind of read that a bit more carefully, but hopefully it should be quite intuitive, where something like that has to happen. Of course, in this order 1 hides some notion of charges, and we can see by how much we should have this being negative in the case of 3D, but more generically, this order 1 doesn't need to be order 1 exactly. It could be 10 to the minus 4 or something like that. Okay, but this, even if it was of order 1 or 10 to the minus 4, it doesn't matter too much. The weak gravity conjecture, this level of negativity in the positivity bounds is precisely sufficient to spoil the applicability of those type of arguments to proving the weak gravity conjecture, because even if this is extremely small but negative, then you can't just say that as black hole evaporated, in the EFT, they will always go within the region of subluminalities, sub-extremality. They can go into the opposite region as well. And so this subtlety, even though it may be extremely small, is precisely relevant for proving the weak gravity conjecture. And I think this is actually very positive because it tells you that the weak gravity conjecture is not just always manifested as soon as you have a standard high energy completion. If the weak gravity conjecture should always be satisfied, then there should be something extra, some additional assumption that you have to impose on your high energy theory for it to be manifested. And so there is something more, I think there is something more to it, and there's something more that we can learn from it, possibly, even if I don't know exactly what it is. But I think this is a positive outcome because it tells us that there's more to be gained from this information. Now, I don't know how much time you're willing to listen to me, but the direction I wanted to go next is understanding what this means in terms of the connection between embedding your theory in a standard high energy completion and satisfying some level of causality or subluminality at low energy. In particular, I would say that because the positivity bounds can allow for a small level of actual negativity, this is directly linked with the fact that the speed of, for instance, photons in the Euler-Heisenberg EFT, which is well known, can have a small amount of what is typically classed as being superluminality, and yet being in no contradiction with causality. So really, we've seen in the case of non-gravitational effective field theory, there was a direct link between positivity bounds, which we say is coming from causality, and the sound speed of light or any low energy phase velocity being subluminal. And this is typically what we typically take a shortcut and say that subluminality is related to causality, or we say superluminality is related to causality violation. But actually, in the context of gravitational effective field theories, if I consider, as I had for the low energy Euler-Heisenberg EFT, as an EFT with a cutoff of the scale m, then I can have an approximate positivity bound that goes like that with a negative sign here. And the fact that this coefficient in the EFT could be ever so slightly negative, this is directly linked to having phase velocity at low energy, which could be typically what we class as slightly superluminal. So this is well known in the context of QED on curved space-time. It's been shown, derived for the first time by Rham and Hathrell in the 80s. It's been shown that if you take photons coupled to electrons, for instance, you can think of virtual loops of electrons that affect the trajectories of the photons. Or if you just work in the low energy Euler-Heisenberg EFT, you have those operators that come in and affect the trajectory of the photons. Now, if you're working on a space-time that spontaneously breaks Lorentz invariance, for instance, around a black hole or something like that, as soon as the Weyl tensor is non-zero, then it leads to speed or a low energy phase velocity for the photons, which could in principle be superluminal. So just due to the curvature, the connection between the photon and the curvatures. So a priori, what is done in a lot of gravitational effective field theories, not for QED per se, but for the gravitational effective field theories, is to try to constrain the operators that you have or the coefficients of the operators that you have in the EFT so as to ensure subluminality for all the species everywhere at low energy. But at the very least for QED on curved space-time, you simply cannot do that because the speed here will always, you can always, this coefficient, just say alpha, depends on those coefficient A, B in a particular way. I'm not going to say too much about it, but they can be related. But they're also related to the polarization of the photons, and you can always find a particular polarization independently of the sign of those coefficients so that the speed seems to be larger than 1, so would be classed as being superluminal.
Sorry, Claudia. So how is it supposed to work? The group velocity is still less than 1, so causality is okay in this curved background, or how?
No, in this case, the group velocity is the same. So the group velocity is also, in that particular case, is also classed as being superluminal. So what we typically say is that the phase velocity can be at low energy can be superluminal so long as the group velocity is subluminal. This is the case for instance, for massive particles. Here I'm dealing with a photon, so it's a massless particle. It's actually not true that the group velocity has to be subluminal, and there are experiments, physical experiments, so not by me, but by physical group, where the group velocity is superluminal. What has to be subluminal is the front velocity, which is the infinite frequency limit of the phase velocity. But typically, we need the group velocity to be subluminal in non-gravitational theories so that it is actually causal. So I will go into explaining why it's okay in this particular case, but in most of the other cases, it would lead to causality violation if you had a group velocity being superluminal. Here, the group velocity is also superluminal as well.
I see. Thank you.
Yeah, yeah. So it is a bit confusing, but so yeah. So let me see how we can make connection with some type of physical observable in this process, and I'll try to make the connection of why it's not an issue in terms of causality. So
can I have a question, like, so when you said the low frequency photons travel superluminally, did you mean within the low energy EFT itself the higher frequency photons are subluminal?
okay, so very good. I consider the high frequency photons will determine what I mean by luminality. So they are, let me say, this is what I mean by luminality. This is the high frequency photons are what are following the null geodesic set up by my background geometry. And the issue is that in this Euler-Heisenberg low energy effective field theory, the low energy photons may travel at a speed which seems to be superluminal as compared to the infinite frequency photons.
And this contradicts the initial slide you showed about the refractive indexes being ordered in a particular way, right? Usually the higher frequency photons are faster.
That's right.
Okay.
That's right. Typically, that's what has to be the case for causality to be preserved. Here, this is not the case, and that's why this seems to be intentional with causality. Yet it's just QED coupled to gravity. It's something that exists in the real world, so surely it has to be okay. And then we know that as you go to higher frequencies, so let me let me go back to maybe. Let me go here. So I'm just computing the trajectories of the lower energy, low frequency photons using the Euler-Heisenberg EFT. That's why I see departure from luminality of the low energy photons. But at high frequency, I'm just reintroducing the electrons, and those operators are not present. So I just have gravity and the standard Maxwell term and nothing else. And I just have the standard QED things. So at high frequency, I have manifest luminality. That's all fine. And it's been shown in a series of papers from Holloway and Shaw that you can connect between the speed at low frequency and the speed at high frequency. And it goes from sometimes being superluminal to being exactly luminal at high frequency. So there's no question that the front velocity is exactly luminal. So in terms of having a front velocity being luminal and consistent with causality, this is absolutely manifest in this case. But we still need to understand how the notion of causality manifests itself at low energy, where we seem to be having low frequency photons that travel faster than high frequency photons, and that seems to be the difference.
And this typically happens in hydrodynamics as well, right? The low energy dispersion might like say something about some superluminal thing, but as you add higher derivative terms, it gets corrected.
That's right. Exactly.
So like you would expect higher, you're saying higher derivative terms should correct this? Like, is that?
Yes,
that conclusion?
that exactly. That's exactly what I'm saying. That's right. There's an infinite number of operators that come here that I haven't written down. When I'm just looking at the low frequency photons, those are all irrelevant. But when I'm looking at high and higher frequency photons and higher than the mass of the electron, then these are very, they contribute, and actually there is some in a way that I know what it is. It is QED coupled to gravity. And I can just go back to reintroducing the electron. All of those operators here, they're just manifesting themselves as having integrated out the electron. But as you go to higher in frequency, all of those just correspond to having the electron as a manifested particle there. And you see that the effect on the speed of light is just that at high frequency, it's exactly luminal. So you could have done it in that picture here, in re-including all the operators, or you can do it in the high energy picture that I'm not writing, but it's here.
Okay, thanks.
Yeah. So when I say that, I didn't write it here. Sorry, I do sometimes afterwards, but there's plus high energy corrections that come here. And so that's why you have low energy photons here, low frequency photons. And of course, it's a continuum, and at high frequency photons will follow some.
So can I interrupt you again? Like, so what I'm confused is, you said within the law EFT itself, for the high frequency photons, you don't need the higher derivative corrections to, or is that by definition?
No, you do. So are you saying because here there's no corrections like the curvature, the momentum of m squared, so it doesn't seem like this?
Yeah. So I thought there's a maybe that was by definition that in the low energy EFT itself, the higher frequency photons are still luminal. That
yeah. So
they don't need the higher derivative corrections to become luminal.
So at leading order, you have the impression you just have that without any frequency dependence of this low frequency velocity. But this is just at leading order. If you go and compute the high energy operators here, their contribution to the speed, you will see that at some point you get some frequency dependence on the speed. And when you take the frequency to be of order the mass, then they are no longer negligible, and you need to include them all. You just don't see it at leading order, but they are there. If you include the higher order operators, they will manifest themselves at some point.
Okay, thanks.
Yeah. So yeah, this you can check explicitly. Yeah. I know typically it's phrased as this is just a second order equation, and this speed is at low frequency, it's exact, but you still have higher order that will come in whether you want it or not. And when you include them, at some point, you'll have some frequency dependence coming into the expression of the speed itself. Okay, so really the key thing of why this is typically linked to causality violation is that if you compute, let me just scatter in a particular example, let me scatter some photons around a black hole, and the high frequency photons will follow what I'll call as the luminal trajectory or the null geodesic set up by the background geometry. So it's not quite, they don't have quite a flat space-time phase shift, but they have a phase shift that I can compute related to the geometry. And now the low frequency photons travel all along a slightly different trajectory because you have to account for the operators that come in the FT, and so they have a slightly different phase shift, and from there it leads to particular time delay. If this time delay is negative, then as compared to those for high frequency, then it's really a time advance, and that is typically linked to a support outside the light cone as set up by the light cone of the high frequency modes. And as soon as you have the smallest support outside the light cone, then you can always imagine a configuration where you're surfing over a lot of it, you integrate it out for an infinite amount of time and space, and you end up with as large a contribution as you wanted to. And as soon as you have a macroscopic contribution there, then yeah, you just build up your time machine and you go and stop this talk before I started talking and everybody is happy. But there seems to be a contradiction there. It is sometimes phrased that this quantity, you can have a time advance so long as the total time accounting for the geometry is positive. And that I would say is not sufficient, because you should really be having a time delay with respect to the high frequency photons and not with respect just to the whole geometry. And actually another reason why this is not I would say a sound argument is that you can consider in principal geometries where this here is negative, and so you can end up with having a negative contribution there, and that's not really the essence of whether it's related to causality or not. It's how
I didn't understand what delta TG was, please.
Okay, so you have this is on the background of the black hole. It's on a, let's say, on a Schwarzschild background. So you're not on flat space-time. So you have correction coming from the geometry itself, which high frequency photons see. So it's given by that. And then on top of that, you have the corrections from the EFT.
Yes.
Sometimes it's argued that this quantity here can be negative so long as they're smaller than the effect from the background geometry. And I would say that's not sufficient, because it would still have a time advance as compared to the high frequency photons. So let me just stick to that point. However, if you look at this type of configurations, we can always estimate the amount of support outside the light cone you can have after having integrated out for as long a period as you can. So for instance, if you are back into the Euler-Heisenberg EFT, as I mentioned before, this time delay is related to the coefficient C that comes into the operators of the EFT, and then the mass of the black hole, the impact parameter, and here's the cutoff, for instance, the mass of the electron. Now, because we're dealing with a gravitational effective field theory, this coefficient, as I mentioned, the positivity bounds don't tell us that they have to be positive strictly, because you have a gravitational exchange amplitude that comes into the gravitational exchange that contribute to the amplitude with the T-channel pole. And so taking all of that into account, it tells us that this coefficient could in principle be slightly negative, so long as it's suppressed by the Planck scale, sufficiently suppressed. And so in this context, if I'm allowing for that coefficient to be ever so slightly negative, it ends up with indeed a time advance, which is related to, and let me put here the Schwarzschild radius, and here is the impact parameter, and m is the mass of the electron, or the cutoff of the EFT, of the Euler-Heisenberg EFT. So this is the maximal time advance you can have in order of magnitude. And a priori, this is something you think you can measure using some apparatus at infinity. You can measure such a quantity. I see no reason why not. However, you need to ensure that.
Sorry, Claudia. That was the difference between the purple and blue lines. This.
That's right. That's right. That's right.
But I thought you argued. I mean, I see, but why can you have any advance at all? Because I thought
yes, very good. I'll tell you why. Very good. So this is problematic, right? I agree, and that has been an issue. But it is an issue in QED. So in QED, I don't know what people thought throughout the ages. I mean, it is something which is manifest in QED, and Hollywood and Shaw have been exploring that for many years and have shown how it is consistent in QED. But we need to understand precisely why you can have a small amount of time advance and still being consistent, because then we're applying the same type of logic to other type of gravitational effective field theories where we don't have this partial UV completion and we don't have a handle on how consistent it is or not. So this is the case in QED, and I need to understand why this is allowed, why nature allows ourselves to have this and still being consistent with causality. So I'm going to tell you why. The reason is I computed this trajectory, the purple line, using the Euler-Heisenberg EFT, and it's only valid if I'm within the region of validity of my EFT. So that means that all the operators have to be under control. And in particular, it means that if I have contractions between, let's say, some curvature invariant and the momentum of the photon that are sent in, this as well has to be under control. So in practice, what it tells me is that if I want to be within the region of validity to compute this purple line, the photons frequency that are sent in has to be small enough. This is anticipated, but what I mean by small enough depends as well on how close to the black hole I want to be, because the curvature becomes the Weyl curvature becomes larger and larger as you get closer to the black hole. And so if I want to say if I sent in a photon with a particular frequency, let me say smaller than the mass of the electron in a particular frame, this is a frame dependent statement, but let me say with a symplectic energy which is smaller than the photon, the electron mass, this is not enough. It tells me there's a finite distance close to the black hole I can be, so that I really remain within the regime of validity of the FT everywhere. And if I get closer to the black hole than that, then I'm going to violate this condition.
Yeah.
But if I have to be sufficiently away from the black hole so that the curvature is sufficiently small, the amount of subluminality I can ride on is also going to be quite suppressed. And therefore, as a whole, this quantity here can never be too large. In particular, it can never be larger than the wavelength of the mode that are sent in.
I see.
So it's never resolvable. It's not about this quantity here. I can design an apparatus where I can compute, I can measure that's okay by itself, but it's with respect to the signal that I sent in, is respect to the wave that I sent in. I'm making all of that in a particle approximation where I'm not considering a wave, but if at the end of the day I'm getting support outside the light cone, which is smaller than the wavelength of the signal I sent in, then clearly I wasn't allowed to use this just particle approximation. So the time advance is smaller than the geometric optics resolution and is not resolvable. And then let me just say it's better than that. So first of all, it's very important to relate this time advance to the frequency or the wavelength of the signal itself that you sent in, and not to simply the cutoff. This is not a Lorentz invariant relation. So I don't know really what I mean by that. And so by itself, this statement is not relevant. It's really relevant to go back to the signal itself. It's all about to do with which wave you're using to probe this superluminality. But as soon as you say that it's not resolvable, that's actually sufficient because it tells you that any type of secular effect, which typically you'd say grows up as t goes to infinity, this grows up and you can have a large contribution from this secular effect. What we're saying in here is that this can never be too big. This is always going to be in some sense smaller than 1. This is having this being smaller than the wavelengths is related to having this being smaller than 1. And so you can always compute your retarded propagator for the EFT, the low energy EFT, perturbatively about the retarded propagator for the high frequency photons. And if you compute your retarded propagator perturbatively, you can't suddenly just create support outside the light cone. If the retarded propagator for the high frequency photons is 0 outside the light cone, and then you construct something perturbatively with it, then all you're going to have is 0 outside the high frequency photons always. You can never have support outside the light cone. So as soon as you've seen that it's non-resolvable, it's actually sufficient to prove causality, to prove the total absence of support outside the light cone.
I see. I see.
So yeah, so all of that was for the story of QED. Now, for us, it was important to understand how we make sense of that in the context of QED coupled to gravity, so that once we have established the criteria within the low energy effective field theory for QED, we can export this criteria for any other gravitational effective field theory, and we can understand what are the constraints we have to impose on the operators so that it's consistent with causality. So I think I'm running very much out of time, but let me just say you can do the same thing for other things. For instance, for gravitational waves, sometimes they seem to be superluminal, And I would argue sometimes that's okay, so long as the level of subluminality is actually not resolvable. And the fact that in gravity, you can have some small level of subluminality and yet have it not being resolvable is very much a gravitational effect. If you are in a non-gravitational effective field theory, and you just are saying flat space-time, then you can have a small amount of subluminality, but you can integrate until an infinite distance. You can just plug in some medium and then surf amongst this medium for an infinite distance, and you can always end up with an infinite support outside the light cone.
Sorry, this is because the black hole makes the wild curvature non-zero only over a certain radius, right?
That's right. That's right. And
so
if you want,
why can't we line black holes up? Have one happen after another after another.
Yeah. So that's very good. But if you have two black holes close to each other, then actually the region in order to remain outside within the region of validity of the FT, you need to be away from both of those black holes. So there's always whatever you want. The thing is, when you're in gravity, when you're in gravitational theory, you need to put stuff in order to have subluminality. But in putting stuff, you have curvature, and you need to be in a region where this curvature is sufficiently small. So this is very different as compared to non-gravitational theories, where you can have a medium there and it creates no curvature, so you're not penalized by the presence of this medium. In gravity, no matter how you're trying to trick your space-time in leading to some subluminality, you also inflict on yourself a higher curvature, so that you can never play within the two. That is not a very rigorous argument. To be honest, we are working on making that much more rigorous. I think we can do that with PP waves, for instance, where in principle you can stack PP waves on top of each other or very close to each other, so as to surf on as much subluminality as you want. But I think what we can see is that when you're trying to play that game, you need to have them sufficiently separated in such a way that for each one of them, you can never have enough support, and even summing of all of them, you're just summing actually just errors. That's what's happening. That's what is happening.
Sorry, could I follow up? I'm sorry. If I understood you right, you said, let's say I take two black holes very far away from each other, then the extra speed up you get from going near each of the black holes is compensated for by some slowdown you get while going in between the black holes. Is this what you're saying?
Something like that, exactly.
But I thought you were comparing the slowdown with the slowdown of an infinite frequency photon. So do you also get a slowdown compared to the infinite frequency photon?
That's right. So what happens actually, it's quite interesting in, I won't show you, but in some examples, what's quite interesting that you get, so let's imagine you send in a radial photon, going towards the black hole. I don't know if you can see me. So it can have some level of subluminality as it goes in, but as it becomes more kind of radial, angular direction in here, then the way the speed affects gets changed, and that's going to affect things as you go between black holes, where you can have some positive contribution and then you'll have a bit of negative contribution, and vice versa. But so far, you're absolutely right that I can tell you in a particular configuration for cosmology, for a black hole, in particular simple case, I can tell you what goes wrong. But what we are missing is a completely generic statement where I can say, let me just imagine some stuff that leads to some subluminality, and for a completely generic curvature, what goes wrong? So we're working on that. So I think there should be some generic arguments, but it's not that.
But do you think the effect gets better? That is, does it get more pronounced by concentrating the matter together? So take two black holes which are separated versus one which has twice the mass, to the extent that you can generate any kind of time advance of order the frequency. Is it really more pronounced when it's all together, the mass is all compact, or when you spread it out? I mean, I was thinking perhaps the most worrisome might be if it's all together in one big black hole. but I don't know.
I do believe that's the case as well. But it's a hard question to answer without going through every possibilities in how you're gonna just think of a lattice of black holes. You want to think whether there isn't a way to kind of pile them up so that you can make the most of it. So
I understand.
The generality of the argument is a little bit tricky to to go through. All I'm saying is that that's the way I understand it in my head at the moment, and why I think it can be generalized. Yeah.
Hi, sorry, can I just ask one question? So the arguments you're giving here is for effective field theory. So you integrate out the high energy mode, then you get a low energy effective field theory. And but if you consider a classical theory which has higher derivative interaction, then these arguments won't. It is still valid. The arguments give that you can have the slight superluminality, and the theories are still okay. If the theories are not EFTs but just classical.
That's right. So then it depends on the strength limit. This is just for the EFT of gravity, but I think can answer in the same way. It depends on the strength of those coefficients.
Right.
So we know that if this coefficient, those operators were coming from having integrated out massive particles at high energy, and this is related to, then this is just mass here, that has to be okay, and it needs to manifest itself at low energy as being okay. Now you can forget where this came from and then just say, I have this EFT. I'm not going to say that it came from integrate out anything. I'm just going to consider it even if you want as a classical theory, that's absolutely fine. And so long as you keep the coefficient of those operators to be of the same order of magnitude, then it has to be fine. Yeah. So once we are in the FTE, we can forget absolutely where it came from. And so you can apply the amplitude argument, you can go back to this EFT and compute your amplitude, which I think then it's very generic and you don't need to get confused about any frame artifact or anything like that. You can compute the amplitude, and so long as the contribution from the T-channel pole subtracted amplitude is not too negative in powers of m Planck, then it should be consistent a priori with causality. But of course,
but if the coefficients are not suppressed by m, let's say there are some order 1 coefficient, so it's just a classical higher derivative series, then is it still possible that delta EFT is less than omega inverse, which is what you wanted to say of causality in that case? Like in the classical theory, could it happen that if delta T is negative, but it is still bounded by the omega inverse, omega being the frequency?
Yes, so it can happen. That's right.
Okay.
That's right. Yeah, it can happen. Yeah. Okay. I can show you in the case of gravity. You can go through the black hole, for instance, and the reason why, at least for one black hole, the level of superluminality that you have is not sufficient to be in tension with causality is the same as what we had for 3D. You can do it for cosmology as another example, and we can go through in that particular setup. I can also show you why the support outside the light cone is always smaller than the wavelength of the signal that you're trying to use to write on this superluminality. So exactly the same resolution or lack of resolution applies, but again, it's in a particular setup. So I think sorry for running so much out of time, but just to conclude, I started with the introduction of the positivity bounds, which I'll argue we can apply on any low energy effective field theory, so as to get some insight on whether or not they are embeddable within a high energy completion. And the connection between the UV and the infrared is made because of the requirement of causality, which at least in non-gravitational effective field theories manifests itself under the notion of analyticity. I didn't say that, but in gravitational effective field theories, the connection between causality and analyticity may be a little bit more subtle, and I still insist on analyticity in gravitational effective field theories. And in all the cases that I have, that seems to be consistent. But of course, this is an assumption and that is welcome to be that you may want to dig into or to remove. Now, because of the presence of a gravitational exchange contribution in the amplitude, you have a T-channel pole, which tells us that the typical coefficient of the pure S-squared terms without the pole doesn't need to be strictly positive. It can be a little bit negative. At least this is my take on the application of the positivity bounds in this context. And so this is directly related to application to the weak gravity conjecture. I would say the causality and analyticity, locality, Lorentz invariance, and unitarity by themselves are not sufficient to always imply the weak gravity conjecture. I would say something else has to come in so that the coefficients in the FT would always be such that in its conservative notion, the weak gravity conjecture would always be satisfied. And then when it comes to dealing with other generic effective field theories, I would say you don't need to discredit effective field theories which operators may lead to a small amount of what is typically lead to subluminality in the gravitational context, because sometimes a small amount of this subluminality may not be in tension with causality. And so you can, this is, maybe I shouldn't write it quite like that, because that's a frame dependent statement. In a frame where you can decouple gravity, then the speed of all the species can a priori account for a little bit of subluminality by an amount which is suppressed by the Planck scale. Okay, so I'll stop here. And yeah, there may be a lot of questions I didn't quite respond, so feel free to ask again.
Thank you very much, Claudia, for a very interesting talk. Let's first unmute ourselves and applaud. We already had many questions during the talk, but yes, if you have any more questions, please go ahead.
Abhijit, can I ask one?
Yes, please.
Yeah. So your positivity proof requires assumption of crossing, right? I mean, the crossing was one of the inputs in the positivity bounds, deriving the positivity bounds.
Requires what? Sorry, I missed.
The crossing symmetry was one of the properties of the amplitude which was used to derive the positivity bounds.
Yes.
So, but
yes.
I was a bit confused, because usually if you have massless, if you have massless particles, then crossing is generally more settled, because there is no gap between the S and the P pole. But if you don't have gravity, if you have photons, then what we usually do is say that, okay, we give a small mass to the photon and we can still apply crossing. But in gravity, we know that we have issues. You just apply mass to the gravity and then take the limit. So is it clear why we can apply crossing to gravitational amplitude?
Absolutely, no, it's not clear. So I guess there's different things. Yeah. So I worked a lot on massive gravity, and you can, the fact that the massless limit of a massive graviton is not the same as gravity. Yes. In this, to be honest, in this case, I don't think this is what is really leading us to the main issues of what we're having. But you're absolutely right that the technical absence of a mass gap does spoils the assumptions behind everything we're doing. So we assume the presence of when we derive the positivity bounds, we assume the presence of a mass, so as to have the Froissart bound. Now, it may not be the case here, and I'm still assuming the Froissart bound, that's one thing, but the absence of technical mass gap and continuing between the upper half and the lower half of the complex plane, this is absolutely an issue. And I think that is also very much related to this whole discussion. I entirely agree. Yeah. No, absolutely. I mean, we're kind of taking a leap of faith that typically the amplitude should be analytic between, even for t between minus m squared and 0, and we can assume you have some finite region for t where you can take it in between and then send it to t is 0 from the lower side. here, actually that gap is 0, so I don't even know what I mean by that.
Right. Right.
Yes, no, absolutely, absolutely. I know if I do the same thing, exactly the same thing for a massive graviton, then I have no issue whatsoever. And the contributions in here will always be positive. I don't have an issue with the teacher report, but also here will always be positive. So yeah, I think you're absolutely right that the absence of mass gap and the fact that we're trying to apply those massive particle arguments to the graviton is the whole issue. Yeah.
Thanks.
Yeah.
Sorry, one question. I didn't quite understand the relation between the discussion of causality with the implications of the weak gravity conjecture. So I thought the weak gravity conjecture implied that the C on this slide here should be positive. Is that so? Is that what gravity conjecture implied?
So I would phrase it slightly differently. I would say for the weak gravity conjecture to be satisfied, C has to be positive.
Yes.
If C is positive, the weak gravity conjecture will follow automatically. So if I can say for any completion that I have, which is meaningful, consistent, C is always positive, then the weak gravity conjecture will always follow, and therefore it's always true, and it's kind of proven. Therefore, it is manifest that it always has to be the case. Now, because I argue that a consistent high energy completion doesn't need to have C being strictly positive, it can be a little bit negative. I would say in principle, I don't see why we couldn't construct a particular setup which seems to satisfy all those positivity type of bounds and still not satisfy the weak gravity conjecture in its conservative version. So of course, if you think of the weak gravity conjecture of saying you need a massive particle which mass is smaller than its charge, then of course it's satisfied. But I don't want to do that. I want to say at the level of the FT, should it be that all the coefficients are such that the extremality condition of the black hole always goes the right way? And I would say that's not necessarily the case. In principle, I can imagine scenarios where that's not the case.
So that would be the scenario concerning QED, right? That's how QED gets out of it?
Yeah, so I mean, QED, I'm just using QED to probe the application of this T-channel pole subtracting amplitude. But QED does have a massive particle whose mass is smaller than its charge. So QED does satisfy the weak gravity conjecture for sure. That's okay. So I can't use QED to contradict the weak gravity conjecture, but I can use some of the lesson learned in QED to imagine another beyond the standard model which may have operators that don't quite satisfy the right relation for the weak gravity conjecture to be satisfied necessarily.
Okay.
It is possible that there are the condition, the positivity bounds is a one-way street, right? If you violate any of the positivity bounds, then you know that you have violated some of the assumptions at high energy. But satisfying all the positivity bounds doesn't imply that you necessarily have a high energy completion, which gives you this theory. So it's possible that it's just not sufficient, and we need something more to be able to prove the weak gravity conjecture.
Okay, thank you.
Could I ask about your criterion of the low energy, the low omega photon not having a time shift compared to the high energy, to the high omega photon?
Yes.
I suppose I wanted to derive this criterion. I think what I would try to do is to compute in the non-gravitational context. So let's say QED on some fixed background.
Yes.
I think what I would have tried to do is to compute a commutator outside the light cone and show that it would be non-vanishing if this was not true.
Yes.
Is this the case? Can you show this? Can you show that if your criterion is not met, then two-point function commutator is non-vanishing outside the light cone?
Yes. So yes, exactly. So you can do that, and that's related to some extent to this. I mean, when you want to compute your commutators, think of it as this retarded propagator. If my criteria is not met, then this thing here can diverge. I can make it so, not necessarily diverge even, but being larger than 1. So I can't do this perturbative argument. And as soon as this perturbative argument is not satisfied, then you need to account for, you need to consider this thing much more seriously. So yeah, you can kind of connect the two. I'm not explaining it like that here, but you can apply all of that by establishing how much support you have when you compute your commutator.
A quick follow-up on that. You know, when you compute an effective field theory, you're integrating out fields using the Feynman propagator.
Yes.
And I would have thought then that that is not sufficient to reliably compute correlation functions in some different time order. That you would need to work on, you know, need to do the integrating out on the contour that you need for that different time order in order to be able to. So I mean, I'm confused about how you can reliably compute a 2-point commutator after integrating out something using using a Feynman propagator. Maybe this is a stupid question. I'm sorry. I mean, just to clarify, to compute a generally ordered correlation function, you need to work along a contour that wiggles around in time. And if you integrated out fields on that wiggly contour, then you can reliably compute anything you want in that wiggly contour. But it wasn't clear to me that you could integrate out things on the straight contour and then reliably compute things on a wiggly contour. Maybe I'm asking a stupid question. Please forgive.
So to reassure you, maybe the way we do it is not as consistent as you would want it, but to reassure you, you can do everything in that picture if you want, where you always have the electron, and you can forget about this low energy effective field theory. These operators are just the leading one that represent this type of phenomenon happening, but you never need to write them like that if you want to. You can always work just at the level of having the electron there and leading to some small corrections for low frequencies and something else at high energy.
Yes, I don't doubt that QED itself is causal. I was just wondering how you could reliably put constraints on these low energy coefficients from this kind of causality argument if you didn't know how to complete it.
So I think that's related to a discussion we've been having for kind of many years, where originally we wanted to say the notion of causality is something which is really related to the infinite frequency phase velocity, and so it requires knowledge about very high energy physics, which is not manifest at low energy. So at zeroth order, how can I say anything about causality at low energy? I think this is related to what you want to say as well. Is that right?
I suppose it is. Physically, I think it's the same point. I was asking a slightly technical point, but it probably is the same physical point.
So I think this is indeed that's a zeroth order take on it. But the reality is, if you are at low energy, I mean, the notion of when you compute your support outside the light cone, and if that support becomes large and macroscopic, then that means that it's even more so within the low energy effective field theory. And so there should be some insight just from the low energy effective field theory about macroscopic support outside the light cone.
Sorry, one comment, Shiraz. One can compute Lorentzian correlators in any order by analytically continuing Euclidean ones, right? So if you do the path integral in the Euclidean space, and whatever you get as low energy effective field theory, if you compute correlators there in Euclidean space, and then analytically, you should be able to analytically continue them and get the desired observable, right, in any order or not.
Maybe there's one counter example. I mean, of course, if you could do it the whole thing, what's not so clear is that the low energy part it determines the analytically continuation of the low energy part. Right. I mean, for instance, people have a lot of trouble computing viscosity in high temperature, in finite temperature field theory from analytically continuing Euclidean correlators. I mean, it could be what you're saying is right, but it wasn't just totally clear to me.
So, I mean, the thing is, whatever you okay, let me go back in terms of this. Just the amplitude. It's not in terms of directly in terms of the commutators, but let me put it like that. So I only have access to some contribution of the amplitude till here, or any physics until here. And I mean, in terms of the connection with analyticity, of course, there's going to be multiple poles that come into that branch cut, but those are all fine and you can accommodate for them. All we're requiring is that there's no poles that come in the actual complex axis itself. That's all we're requiring. So maybe let me go in here. I know this is at the level of the amplitude and not quite commutators, but can we make the connection between what you want to say at this level? Because I think you want to say there's something wrong. There's something else I should know about these arcs. Is that kind of related to what you want to say?
I'm not completely sure. The technical question was, can you use the Euclidean effective field theory to reliably compute commutators at low energies? You can certainly use it to reliably compute time-ordered correlation functions at low energies. It wasn't so clear to me you could use it to reliably compute commutators at low energies. Maybe it's a stupid question.
Yes, I would say yes. I would say perturbatively yes.
Okay, thank you.
Yeah.
Okay, are there any more questions?
Just one last question, just following up a little bit on the previous discussion. So if you take just a classical theory like higher derivative gravity theory, like the one that C and Z consider, is the statement that there is a space of parameters where the theory is still okay. It looks a causal, but it is not. It doesn't violate causality. Is that correct way to understand the result?
That's right. But it may require the magnitude of those operators, the coefficient of those operators, to be very small. But I would say, I would claim just compute the amplitude and ask for what comes into the positivity balance to be not too negative. And so long as this is satisfied, I would think it'd be consistent with causality.
And that you think that will remain true even if these operators are not like scale suppressed? It's a purely classical theory as opposed to
well, if they're not suppressed, you can have cases where then it's negative and too negative.
Yeah, that's right. But if there is a space of parameters you're saying where it may be okay.
Yes, but you will see, I mean, it's implying suppressed, so it still has to be quite suppressed. In this
case, I agree. I was just asking in the context of a purely classical theory. Like, I thought E and Z do not consider, maybe I understood it wrong, that they don't really look at effective theories, but just look at higher derivative classical gravity theories that they want to rule out, so that the coefficients are not implying suppressed.
Yeah, so I think if the coefficients are not implying suppressed, then you can compute the contribution to the amplitude, and it will be too large. You'll end up with having contribution which are too negative, so that you'd think it's gonna be violated.
Right.
Yeah.
So in that sense, the E and Z criteria is still okay, you're saying. I mean, for the question that they are asking, classical.
That's right. I would say it's still okay. You don't need to think of it as. You don't need to know where it came from and whether you want to think of it classically or as a quantum EFT. It doesn't matter. You can still apply the same, because at the end of the day, that connection with causality is just a classical one.
Right.
Yeah.
Thank you.
Okay. If there are no further questions, let's thank Claudia again.
Thank you very much. Thank you for the questions.
Thank you.
Thanks.